you will have three lecturers. Okay, Dr. Nizum already done his 7 weeks part. Then another 3 weeks under 3 weeks I will conduct the class. Then another 3 weeks Dr. Tay will conduct the class. Then another 1 more week, final week, we will be doing assessment, okay, for my part and Dr. Tay's part, okay. I believe Dr. Nizum already explained all that, so I think I don't want to, I'm not going to explain all that again. Just that class next week, Thursday, most likely Dr. Tay will be teaching the class because, I can't make it. Then the following week, I'll be teaching on the Thursday for another 2 more weeks. So something like that. But we will be keep update things in the WhatsApp group, okay? So far, any questions, class, before I start the class? Any question from anyone here? Anything that unclear or you are confused with? Anything, class, so far? We haven't started yet, right? So probably you won't have questions at the moment. Am I right? Anyone?
No question.
No questions. Okay, great. Okay, so class, now let me share today's lecture notes. Yeah, I believe all of you all by now you should have your lecture notes with you. Okay, so let me share now. Okay, class. So today, what we are going to learn is, class, okay, I'm going to explain about the basic principle of chromatography separation before we go further into gas chromatography, into high performance liquid chromatography, and about sample preparation method and what is trace chemical analysis. Before we go for all that, okay, chromatography separation, okay, the theory behind the chromatography separation is very, very important, and all of y'all should know the basic of it, okay. So class, now as for today, okay, so what you are going to learn, the outcome, the course learning outcome should be, okay, you should be able to understand the general concepts and principles of separation in chromatography technique, and then understand the efficiency of the separation. Example, resolution, plate theory, rate theory, especially Van Dimter theory, okay? And then apply the chromatography equation in solving problems, okay? And then plot and interpret the chromatogram. So basically, class, I will really make sure you guys understand what is resolution, what is plate theory, what is Van Dimter theory, all these you have to really, understand so that you won't have any problem later as we go. Okay, so now class, class, so far so good? All of y'all can hear me clearly?
Doctor. Yes,
Yeah,
doctor.
okay, good. So class, I think I won't do this online class for very long. I won't do for 2 hours because I don't prefer online class actually. Okay, so I prefer to do it physical class, but no choice, I have to do it online class for this week. So class, now when we are talking about method of separation, yeah, so when we are talking about method of separation, so class, basically method of separation, we have so many methods of separation. For example, distillation is one of the method, extraction, chromatography, electrophoresis. So all these are considered method of separation, but the basis of the method is different. So for example, class, distillation. Distillation is based on the differences in volatility of a compound. Well, extraction basically differences in the solubility of two immiscible liquids. For example, liquid extraction. Okay, we will call this LLE. Okay, LLE. So liquid extraction. Okay, when we are talking about the chromatography and electrophoresis, so this one involves samples that are multi-component and complex. For example, class, in chromatography, we can able to separate few peaks as a mixture, and we can able to quantify what is the concentration of the each peak as well. For example, paraben. the simple one, yeah, the one that you are using in your practical. Okay, so class, like for example, methyl paraben, ethyl paraben, propyl paraben, benzyl paraben, we can actually separate that just one run, class, in a mixture. Where in a mixture we can able to separate it into different component. So that is the advantage of this chromatography method. Okay, so now class, okay, let's move to the definition of chromatography. So what is basically chromatography? So class, basically chromatography is actually a separation method where the component in a mixture will be separated, to be separated are distributed over the two phases. For example, a stationary phase and a mobile phase. So class, again, yeah, mobile phase is a fixed phase. Okay, mobile phase is a fixed phase, while stationary phase is a fixed phase, while mobile phase is a moving phase. Okay, okay, it moves in a defined direction. For example, class, in HPLC separation, the analyte that moving through the HPLC, for example, HPLC or GC, end of the day, it must go through column, column. So column, we will have stationary phase over here. Okay, for example, this is our stationary phase. Just imagine, yeah. So mobile phase will bring the paraben. For example, the analyte here, the compound that we are separating, let's say paraben. So the paraben, the mobile phase will bring the paraben, then each paraben will be interacting with stationary phase. Okay, so once it's interact with stationary phase, then the paraben that has strong interaction will release later. That means elute later. The one has least interaction will elute fast. So the one that elute fast will elute first, followed by maybe this is the first retention, second retention, third retention, fourth retention. Meaning that class, in a separation, for example, HPLC or GC, it's all time, like first 2 minutes one compound separated, first 3 minutes another compound, first 5 minutes, and first 7 minutes. So it's something like that, class. Compound 1, compound 2, compound 3, compound 4. So based on all these class here, so compound 1 has least interaction with stationary phase, compound 4 has strong interaction with stationary phase. That is how we will define. Okay, so especially when we are running GC, just one moment, class. Yeah, someone here. May I ask where we can get lecture note? Oh, okay. So I think class I already shared. Oh, I think for those joined later. Okay, thank you, Emilia. Emilia, is it okay for sharing? Yeah. Okay, thank you for that. Okay, so class, now in that case, yeah, so the one that elute first has least interaction with stationary phase. So class, again, stationary phase is something that don't move. That is stationary phase. The one that moving we will call as mobile phase. So in HPLC, the one that moving is actually a solvent. It can be organic solvent and water as a mixture or buffer solution, whatever. So that is a liquid we will define as a mobile phase. Well, in gas chromatography, mobile phase will be gas. Okay, usually the gas flow, we have to play with the temperature programming and gas flow in gas chromatography in order to separate the compound. And GC is based on volatility. HPLC is based on polarity. So it's two different things, class. So usually polar compounds, we use HPLC or LC, and non-polar, more hydrophobic or volatile compound, usually we run by GC. So class GC is based on volatility. So the one has a compound, for example, 5 compound. Okay, the compound, which compound has very low boiling point will elute first. So that means that compound might be interact very uh, not very strongly with the stationary phase, and it will elute first compared to the compound that will interact very strong with the stationary phase will be elute late, but the one most likely the compound that has very high boiling point. So GC, again class, yeah, gas chromatography is based on volatility. Okay, more volatile a compound, is very easy for us to separate. So usually class, those compound that very volatile, we can actually find through their structure whether the compound is volatile or not. Usually volatile compound, we just go for gas chromatography. Okay, and the one that has very least boiling point, always will elute first. That means will come out through the column first, compared the one that has high boiling point. That means class, when has high boiling point, the GC temperature, that the one that we are adjusting, when we are running gas chromatography, we have to adjust a temperature. Usually how we will adjust the temperature, basically we will compare the analyte. That analyte means class, the compound, for example the paraben. Okay, just keep it paraben as an example. So basically class, paraben has about 4 analyte. So each analyte, I mean like methyl paraben, ethyl paraben, propyl benzyl, so but 4 analyte, right? So that 4 analyte, we will see which one has boiling point, low boiling point. I mean, what is the range of the boiling point from the low and the high? So which compound has very low, which compound has, so basically we want to make sure we cover the temperature of that each analyte. Okay, each and one analyte of that 4 analyte. Yeah, we want to make sure the temperature programming that we are choosing, basically it should cover the analyte's boiling point. So that class, when we are doing the temperature programming, as the temperature increase, the analyte will elute. So that is the concept of GC. Okay, so but HPLC, we really think of the polarity and we will explain through the interaction. Okay, but the basic idea class, just put it like this. Yeah, the compound that has strong interaction with stationary phase will elute late. The compound that has least, that means weak interaction, will elute fast. Okay, elute fast means it will appear in the first, okay, in your GC or chromatography. Okay, this is your chromatography. Yeah, we will call this as a chromatography. So the one elute first has least interaction with stationary phase. That's why it can come out very fast compared to number 4. Number 4 has very strong interaction with stationary phase. So basically class, interaction is depends on the how polar is your analyte, what type of, is it van der Waals forces or hydrogen bonding, it depends. Okay, too strong interaction also is not good with stationary phase, because some of the compound will just retain in the column. Okay, so that is the basic concept of chromatography. Class, so far so good? Class, so far so good?
Yes, doctor.
Yes,
Sure.
doctor.
Okay, I'm a bit worried because this is online class, so that's why. So class, now look at this. Okay, when we are talking about chromatography process, yeah, so look at the column here. Okay, so class, just imagine, yeah, imagine when you are, suppose when you are running your HPLC or GC, I think we should, the lab assistant or the lecturer have to show you where is the column. So if you see, what happened is inside the column, the sample that we are running, the mobile phase will help to carry the sample, go into the stationary phase, into the column. So inside the column, we already have a stationary phase. This is our stationary phase. Stationary phase is a fixed phase. It's not moving. It's a stationary phase, and it do have a solid and liquid as well here, but it's attached, so it won't move. Okay, so we have stationary phase here. So the mobile phase, either it's a liquid or the carrier gas, will help to flow through the column. Okay, basically when the sample go through the column, pass through the column. So eventually each compound, let's say in the sample, usually HPLC, GC, we run extra mixture class, yeah, mixture, because we are not running UV spectrophotometer. UV spectrophotometer, yes, we do individual measurements, but HPLC and GC, the best thing about that is we can able to separate multiple compounds in one run. So that is the advantage of that. So the sample can be like, you remember 10 sample as a mixture. We prepare standard in a mixture so that we can able to run together. Okay, together. So maybe 10 sample we run. So end of the day, we will get around 10 peak. By right, around 10 peak we should get lah. Okay, maybe 10 peak, something like this. We will get 10 peak. So class, based on this, we can see this compound has very less interaction or very weak interaction with stationary phase compared to this compound. This compound can retain longer, even though the mobile phase is keep flowing. So bringing the sample is like keep like flushing, like pass through the column, and then the carrier, for example, for GC, the carrier gas is actually helping to bring the sample out column. So this is the idea, class. Okay. Okay, now this is the chromatography process. So now, class, okay, let's move to the definition. So class, stationary phase, as what I explained before, stationary phase is the one that stays inside the column or on a solid surface. So that is what we will call as a stationary phase. It's a flat sheet, class. Okay. Well, mobile phase is actually a solvent that moving through the column. It's like a carrier lah, carrier. So usually, class, in GC, the mobile phase will be helium gas. HPLC, it can be liquid, either water or organic solvents. Okay, usually we don't run pure water. It's actually combination. It's like maybe 70, 30, something like that. Like 70% of water, 30% of organic solvents such as methanol or something like that, class. Okay, so it's actually combination in a mixture. We will run that in a mixture. Okay, so that is the mobile phase. Okay, now, so class, any chromatography system, it actually composed of stationary phase, mobile phase, and mixtures to be separated. So this is actually basically your sample. Okay, so basically this is your sample. So class, this is actually HPLC column. So we will call this as a column, and inside the column, it has stationary phase. Okay, and this is actually stationary phase fixed on a solid surface. This is actually TLC, yeah, thin layer chromatography. Okay, the type of chromatography, we have gas chromatography, high performance liquid chromatography. We do have a thin layer chromatography and supercritical fluid chromatography as well. Okay, so class, basically the general principles of chromatography is components of the mixture are carried through the stationary phase. Basically, class, the compound, the component of the mixture are being carried through the stationary phase, actually with the help of mobile phase. Mobile phase is actually as a carrier, class. Okay, I can say this as a carrier lah. Okay, so as a carrier to carry the samples. Okay, so the separation basically will occur due to the different affinity of the component with the stationary phase and mobile phase. So basically, class, affinity means like how strong the analyte is actually binding to the stationary phase. So that is the idea lah. Okay, and class, again, yeah, those compound that strongly retained by the stationary phase will move slowly with the flow of mobile phase, well, the one that weakly held by stationary phase, that means that very weak interaction will travel rapidly. So when travel rapidly, it will elute first compared to the strongly attached one, maybe elute later. Okay, so the differences in mobility will cause the sample components to separate. So this is the idea of chromatography. This is the idea of chromatography. Okay, so class, you can look at this picture. Yeah, so when you look at this picture, you see here, okay, at T0 and at T20. So if you look at this, yeah, so when the injector, we inject the sample at the injector port. So when the sample go through the column, so this is the mixture, yeah, combination of few compound. The mobile phase are keep flowing, and finally the output from the column will go to the detector. So as time move, class, yeah, as time move and time move here, you see each compound will be separated according to, this is considered most interacted with the stationary phase, this is least interacted with stationary phase. So this one will elute first compared to this. Okay, this one will elute later. Okay, so this one has, I can say, moderate level interaction with the stationary phase. So class, if you look at this chromatogram, class, again, yeah, FTIR spectra, UV spectra, we will call that, we will address that as a spectrum. Well, HPLC and GC, we will call that as a chromatogram. It's different, class, yeah. HPLC and GC, the results or the peak that we are getting, we will call as a chromatogram. Okay, we won't say, hey, why your peak like this? No, why your chromatogram is like that. So when we are talking, class, we have to be very clear with what we are talking. Okay, so when HPLC GC, basically it's actually a chromatography result. So class, basically, if you look at these component bands here, so the plot of the component concentration. So class, basically when the sample enter into the column and exit to the with the column. So basically, if you look here, so we will get a peak like this, you know, in HPLC and GC. So at this point, actually, the it has a high concentration of the analyte, and then it will go down. So this is what the basic concept of the chromatography. Okay, so class, now if a detector that responds to solute concentration is placed at the end of the column during elution, well, it signal, okay, so something like class, okay, here we have our, sorry, we have our peak area. We will call Y is a peak area, X is a retention time. So usually when we are separating a compound, is actually will be separating like this lah. So this one is actually a peak area value. Okay, Y is actually peak area, X will be retention time, and such plot we will call this as a chromatogram. Okay, so now class, for example here, the peak position, basically the peak position actually used to identify the components. Peak area is actually to identify the each amount of the component. For example, class, peak area we will use for quantification. We will use peak area, okay, rather than peak position. We don't use peak position for quantification. Peak position is actually just for profiling, for screening to see whether what analyte it has. This is peak profiling. This is separation we will call. But we will use the peak area to determine the amount of the component or the analyte. So that is the difference class. Okay, so you should know about all these. So class, now this is very important here again. So class, if you look at these useful terms, okay class, process in which the components that wash out through the stationary phase by the movement of mobile phase, we will call at elution. So class, in a column, when the mobile phase bring the sample pass through the column, so when it's exit the column, so it will give you a peak like this. So we will say elution. So class, in this compound, I can say A elute first compared to the B. Okay, so A elute first compared to B. So B has strong interaction with stationary phase. So elution is the washing. Consider, we won't say washout, might be very technical, but in terms of scientific class, we will call that as a elution. Elution is something like a where the components are washed out through the stationary phase. So basically, class, if we when we pass through the stationary phase, it's like all the component, they will be like have some interaction. So we will keep flow with the stationary phase. Either for HPLC we use liquid, for GC we use gas. So we will keep flow, so that that flow basically will consider wash out, or you know, will force the analyte to leave the stationary phase and go to the detector to read so that we can able to get the chromatogram, the separated chromatogram. So for that is what we will call as a elution purpose. So the mobile phase we will call as a eluent. Okay, so class, remember, yeah, for HPLC or LC, we will call mobile phase as a eluent. Okay, the component that leaving the column we will call as a elute. Okay, elute. And the solid that dissolve in liquid we will call as a solute. Okay, the solid that dissolve in a liquid. So what is the solute? The solution that dissolve the sample. So the sample, the chemical or the substance that we are determining in the analytical procedure, we will call as a analyte. So class, basically paraben is the analyte. We dissolve paraben in a methanol. So the solute is methanol. Okay, so that is the difference. Clear or not, class? So far so good. So far so good, class. Class.
Yes,
Okay,
doctor.
doctor.
Okay, good. Okay, class, now retention time. Okay, so class, again, when we are talking about retention time, so again, your X will be your time and Y will be your peak area. So class, retention time for the analyte to pass through the column, or the time for the sample to inject to the detection. So basically, class, TR is actually retention time, TM is actually void time. So class, this void time usually in GC we can't find unretained peaks. So consider something that unretained will elute first. In GC very rare, we can't find this, but in HPLC yes, we can get this void peak. Okay, so each analyte class will have different retention time. It actually depends. Okay, so TR is retention time, TM is a void time, and TS is actually adjusted retention time. Okay, later when we do the calculation, we will understand things better. Okay, so class, okay, now okay, this is the one class, yeah, TM. So here the TM is actually usually we can get it, we can see that in HPLC peak. So we will call this TM is actually a white time or dead time. So this is actually the time of non-retained compound spent in a mobile phase. So consider it doesn't retain at all in the mobile phase. So immediately it will just elute from the column. So the amount time that a non-retained compound spent in the column, or the time taken for the mobile phase to pass through the column. So it's actually, uh, we will call this as a void time or dead time. Okay, so now class, adjusted retention time, usually TR or TS is actually a time in a compound spans in the stationary phase. Basically TR prime is equal to retention time minus with the void time. So basically adjusted. So when we minus TR minus class, TR is this one, yeah. TM is this one. So when we minus TR minus TM, we will get TS. Okay, sorry, TR. So TR minus TM. So this is actually adjusted retention time for each compound. So TR is the difference between TR and TM of the compound. So for example, this is the TR and this is the TM. So when we minus, so we will get the adjusted retention time. Okay, so sometimes we have to do correction when we are doing calculation. Sometimes we no need to do. So the one we eventually when we are learning. So I'll be explaining all that. So now class, okay, retention time or capacity factor. So class, if you look at this here, K is actually used to describe the migration rate of the solute on the column. So K prime for the analyte is depends on, the formula is TRA minus TM, this is a void time, and this is also TM is a void time. So basically class, retention time for the A, for example, just imagine this is A. So the retention time for the A is, this is the one class. So you have to just replace, I mean, you just have to input all the values here, including the TM value, to calculate the retention factor or capacity factor. Why we need to calculate that? Because when we have retention or capacity factor, basically we can able to describe the migration rate of the solute on the column. So we, to see the migration rate, we have to calculate this class. Okay, and if you see K can be derived from chromatogram, basically class, a larger K, which is like more than 20 to 30 is actually good separation, but increase the elution time. That means class, when we are doing a separation, we want to separate a compound in short time. For example, this is 2 minutes, this is 4 minutes, this is 6 minutes, this is 8 minutes, done. A. So in another case, B, let's say B, I'm separating this compound, but okay, let's say the same thing I'm separating, but this is I'm separating at 8, I'm separating at 9, 12, and 15. So if you see class here, the same compound, but here in A, method A, I'm separating within 8 minutes. Method B, I'm separating within 15 minutes, which is like I'm wasting the mobile phase. For GC, for HPLC, I'm wasting the organic solvent. Well, for gas chromatography, I'm wasting the gas. So we want the elution time to be lesser. So that means we can run in shorter time. So that's why a very large retention time also not good, but a good separation class, usually the retention time should be between between 2 to 10. So this is what we want in separation basically. Okay, so now let's move to the selectivity factor. Okay, so class, maybe before we go to selectivity factor, maybe we can take 5 first, yeah? Okay. Okay, class, we can continue. So now, class, let's move to the selectivity factor. So, class, basically, selectivity factor, um, why we have to study selectivity factor. So basically, selectivity factor will describe the separation of two species. For example, A and B on a column. Yeah, if let's say we have two compound A and B, we have to calculate the separation factor to see the separation is good or not. Okay, there is usually separation factor is greater than one, but if it's equal to one, is actually we will say that the compound is not cannot be separated. It's something like maybe over we will either overlapping or something like this. This is considered we cannot separate this compound. Okay, usually the higher the selectivity, the more separation between the two compounds. Okay, so class, how we are going to calculate the separation factor? So sorry, selectivity factor. So selectivity factor, we will use retention time minus with the void time. Again, class, yeah, retention minus void. So this is the formula for selectivity factor. Okay. So now, let me move to the efficiency of separation. Class, basically, when we are talking about efficiency of separation, the two factors that affect the components, it's basically the difference in the retention time between the peak, okay, and then the peak width. So class, basically, okay, the meaning is class, okay, when we are separating compound A is well resolved, compound B is well resolved. So this is a good separation. If let's say I'm separating a compound here, separating and it's not even well separate, this is not a good separation. So class, like this, we can able to quantify. Okay, we will quantify this. Okay, the peak area of each individual peak. But here, since this is like not well separated, not well resolved peak, we will call this as not well resolved peak. So in that case, this is consider not not good separation. This one is actually a good separation. So class, basically the difference in retention time between peaks, okay, further apart, better separation. Okay, and peak width, class. So peak width is basically, this is peak width. Okay, W, we will call this as peak width. So class, an efficient peak usually, class, yeah, okay, let me draw here. An efficient peak basically will give you a narrow peak. A narrow peak means something like this, class. We don't want a broad peak like this. This is not a good peak. Okay, in chromatography technique, if the peak is very broad, okay, we will call that as a very broad peak, and the separation is not good. Okay, the peak should be narrow, okay, so that we can say the separation efficiency is good. So class, basically, uh, this difference between the retention time, that means that how further apart each compound, and how well the peak being resolved, like how narrow is the peak, all that, class, yeah, is actually will it falls under Gaussian profile. So according to the Gaussian profile, a peak should have this is the ideal theory of the Gaussian peak. So basically, if you look, this is what we will call as height. This is actually height, and this is retention time, and this W is the width, peak width. Yeah. So this is peak width. So this is actually ideal shape of a peak. Okay. So this is the efficiency of separation. Okay, class. Now, this is very, very important. Yeah. In separation, actually, we will really see the resolution. Okay, so how well the separation of the two peaks occurring. So this is very, very important. So although the selectivity describe the separation of the peak, but it does not take into account of the peak width. Okay, so even though selectivity is important, but selectivity does not consider about the peak width, but resolution is really about the separation. So class, compared to selectivity factor, actually resolution is even more what I can say is resolution is even more important when it comes to separation compared to the um, selectivity factor. Okay, because through resolution we can say a compound is well resolved or not. For example, okay, how, okay, let me explain how we will be calculating the resolution. So class, resolution basically we will calculate, this is the formula, 2 times, okay, resolution between two compound, yeah, tr2 here, tr1 here, over wb1 wb2, we just plus those, this is resolution. So class, if you see here, when two peaks are overlapping to each other, okay class, okay, just focus class here, when two peaks are overlapping each other, for example compound A and compound B, it does not resolve class. So the separation is actually 0.5. If the peak separated very well, uh, you know, like this one is a very good peak. Okay, it's separated very well. So class, usually resolution should be more than one, but even more than one, we don't accept. The higher the resolution, the better the separation. So usually class, resolution should be 1.5 and above. Okay, then consider it's a good separation. Okay, not class. Class, so far, so good. Class, so far, so
Yes,
good.
doctor.
Okay, doctor.
Sure. Okay. So now, class, resolution 1.5 actually represent the baseline resolution or complete separation of the analyte. This is actually ideal case lah. Okay, but most of the separation 1.1 is considered okay, but but in practical we don't accept that. Okay, so class, I have given sample 1, sample 2, sample 3, calculation. All these I prefer to do, we can actually do during the next class, okay? I'll be doing this calculation next class. So let me explain about the column efficiency. So class, now, when we are talking about column efficiency, class, for HPLC, for GC, there are so many columns, class, and the column is actually depends on what type of analyte that you are going to separate, what type of analyte you are going to, and so consider if your analyte is a polar analyte, then your column should be polar. If your analyte is a non-polar, then your column should be non-polar. So it depends, class, what type of column you are using for what type of analyte. There are so many column, but the most common one here in our department, we are using C18 column. So C18 column is actually a non-polar column. It's a hydrophobic column, like I can say non-polar column. And it's easy for the separation. So we are using C18 column. So class, in the column, basically this is very, very important, class. Yeah, please pay attention. When we are talking about the column efficiency, basically column efficiency we can express as theoretical plates, plate height, or height equivalent to theoretical plate, HETP. So class, now if you look at this column efficiency, H and N provide useful measures to compare the performance of different column for a given analyte. So class, if you look here, column efficiency is expressed as a number of theoretical plate and plate height. So class, let me explain. Okay, what is theoretical plate number and what is plate height? Class, don't get confused. Yeah, it's either plate height or height equivalence to theoretical plate, HETP, but usually we use HETP. Okay, there are two things here when we are talking about column. How we are going to decide? Okay, for example, you have a compound A and you have to separate the compound A and you are looking for a good column. So if you ask me, I will ask you to find, okay, when you want to choose a good column for your compound, please look at the theoretical plate number and please look at the HETP number. So the theoretical plate number should be higher, HETP number should be lower. So consider that is a good column for the separation, but for that particular analyte. Okay, it depends. Okay, why? theoretical plate number should be higher, why HATP should be lower. Okay, I'm going to explain that. So far, so good, class?
Okay, doctor.
Okay, so H and N basically to provide useful, it's very, I mean, basically it's to provide very useful measures to compare the performance of different columns for a given analyte. So basically class, theoretical plates is actually, we can imagine class, okay, just imagine this is our column. Our column, as I told you, this is your stationary phase. Up and down is your SP. SP is stationary phase. Your mobile phase will bring your analyte and mobile phase will flow through this. Okay, will bring the analyte and flow. So class, basically the stationary phase has column. So that column basically we will say like it has a divided like a partition like that, you know, class. This is what theoretical plate number. So basically the analyte will go through one plate to another plate one. So there will be some equilibrium process there before it jumps. So it's basically we will call as this is as imaginary segments. Okay, and it's called as a theoretical plate number. So n is actually a number indicating how good a column is for the separation. So class, we can't see the plate number, you know, in generally we can't see the plate number, but theoretically we should imagine actually the column as these theoretical plates. Okay, so these theoretical plates like theoretical plates like the mobile phase is actually will bringing from one theoretical plate to another, one to another. So class, in theory, if you look at this, yeah, this is the column, theoretical plate number. So the analyte is actually moving through from one plate to another, one plate to another, one plate to another, one plate to another, something like that with the help of mobile phase. Okay, so there will be some equilibrium process between the mobile phase stationary, I mean the analyte, the solvent of the analyte in that place. So the analytes that move down the column by the transfer of the mobile from one plate to the next. So basically class, that equilibrium is the one like pushing the analyte from one plate to another, one plate to another throughout the column. So basically class, the plate actually does not exist, but there are we will call that as a figment of the imagination that help us to understand the how the column work. So basically class, the larger the larger the n of the column, the better the column will be able to separate the compound. Okay, because n is actually few hundred to several hundred thousands, you know, class n. So basically a column with higher n, okay, are more efficient and have a very narrow peak at the at retention time. So basically then a column with a lower n number. Okay, so basically a column with I n has more, it's more efficient and has more narrow peak compared to the lower n. So that is the difference class. Okay, so now, so class, this is actually n. There is a formula to calculate n as well. This is the formula class. Okay, n is equal to 16 tr over wb squared. So basically, tr is your retention, wb is actually your peak width. WH is actually middle peak width, but usually we don't take WH, we use WB. Okay, this peak width power 2. So and n is actually specific for each solute in a given column. And basically class, as retention time increases, it increases the n value as well, because if you see n is equal to 16 in bracket tr over wb square. So basically when we increase the n, when the retention time increase, eventually the n is also will increase. It depends class. Okay, so now okay, apart from all that class, yeah, n is also depend on the length of the column. So this is the formula of that class. Okay, again, n is your theoretical number, L is your length of the column, and HETP is actually plate height, or this is the one class, plate height or height equivalent to the theoretical plate. So this HETP, we should maintain the HETP lower class. Okay, how okay, here I would like to just to, I'm trying to explain here, class. Basically, if you're if you want your hand larger, your HETP should be lower. Okay, basically for a good separation, we want N to be larger, HETP to be lower. So now class, if I want to, explain about the N, yeah, so N to obtain the certain resolution, for example, N1 and N2, if you see here, N2 better, the theoretical plate number for the N2 is better compared to N1 because the peak is very well resolved compared to the N1. Okay, so that means that the resolution better here, as well as the N value is also better here. So class, to improve the resolution, what we can do, we can increase the length of the column and increase the N value. So now class, here basically we want, okay class, just to make it simple here, the theoretical plate number, which is N, should be higher, So according to this formula, if we want N to be higher, the length should be higher as well. The length of the column should be higher so that our N will be higher. But HETP, which is the plate height, okay, HETP again class here, look here, your HETP HETP is actually a plate height or height equivalence to a theoretical plate. So the HETP should be lower. The plate height should be lower, but the length should be higher. So it's two different thing class. This value HETP should be lower, L should be higher, so that the N should be higher. So class, when your N is higher, your separation is good. Okay, the example of this class. So here the N is lower. So that means class, if I want to use theoretical plate number, I can say here N is lower, here the N is higher, maybe RS here lower, resolution is also lower, maybe less than 1.5. Here the resolution is more than 1.5 or 1.5. That's why it's actually well resolved here. Okay, we can see the difference here. By lengthening the column, it can also increase the theoretical plate number. So class, basically, if we look at this formula, okay, height equivalence to theoretical plate, which is plate height, or we will call either height equivalence to theoretical plate, okay, HETP, is basically approximately the length of the column that required from one equilibration of the solute between mobile phase and stationary phase. So class, to compare the efficiency of column with different length, yeah. So basically the column that has longer, I mean, the longer the column, basically the N will be longer, but HTTP will be lower. So class, basically here, this is the one. So the smaller the H, the narrow the peak width. So when the HTTP number lower, basically resolution increases, N increases, and of course the L is also should be increased lah. Okay, should be length. The length of the column also should be higher so that we can able to get a larger N. Okay, so class, basically a greater separation occurs with the greater N value, and HETP should be smaller. So this is the ideal concept of separation class. Okay, so this is the relationship of all the formulas here, but you class, again, yeah, you no need to memorize all these formula. I will tell you which one is important. Okay, so don't stress up yourself, and you guys can try all the sample 3A, 3B, 3C, and sample 4 as well. So class, and I will we can discuss about all these sample next week. Next week Thursday, if next week Thursday or the following week, I need to double confirm with Dr. T about the class here. So column performance. So class, this is all about the column performance, and Van Dimter equation is, it's about the different story. But I think I don't want to make it very long now. So class, now we have about half an hour to go. So what I'm expecting you guys is I want you guys to start to do the problems, the sample problems, okay? The calculations, okay? You can just use the balance half an hour to refer, just refresh whatever we have learned so far. Okay, I don't want to, put so much in today. So I'm worried, too many things. The second story is actually more towards why we are getting broad peak and about the Van Dimter theory. So it's better for me to explain face to face, okay, that theory. So for now, try to understand the basic concept of chromatography and try to do the calculation. I can explain, we can do the calculation on that Thursday. Is that okay, class? Class, so far so
Okay,
good?
doctor.
Okay, yeah.
Yes,
So
doctor.
class, any questions, class, so far? Any question, anything that confusing, or do you have any question to ask me? Not personal question lah. Something regarding our subject matter. Do you have anything to ask, class?
No, doctor's class very clear.
I can't hear you, sorry.
Doctor's class is very clear. No
Oh,
question. Hey.
okay. Thank you so much for that. So class, I think if no question, so I think we can end our class for now. Okay, it's a Friday, and I think I don't want to stress you guys too much. So it's okay, class. Slowly we go, but we make sure we achieve our target. Okay, so that's all, and don't be stressed about the assignment. I won't give something that to trouble you guys. We can think about that. I will explain during our face-to-face class about the assessment. Most likely I will talk to Dr. Tay to make it online because I want another one more class. Okay, so that's all, class. Okay, thank you so much. Okay, bye bye. Have a good weekend, class. Bye bye.
Thank you, doctor.
Thank you.